Hi guys, so today we're going to be doing exponential and binomial distribution. Before we get started with example 1, let's take a look at exponential distribution functions. Okay? So you can use exponential distributions to predict the probability of events that are based on time. Okay? They are most commonly used to measure reliability, which is the amount of time that a product lasts. Okay? Exponential distributions apply to situations where the time spent on an event or the amount of time that an event lasts is important. Okay? And so they're represented by the following two functions. Okay? So the formula f of x equals e. We talked about e before, right? This is our natural number. This is our 2.718281828, etc. Okay? To the negative mx. Okay? So this gives the probability that something lasts longer or costs more than the given value x. Okay? And then m is the multiplicative inverse or the reciprocal of the mean amount of time, the average amount of time. Okay? The other one, the formula f of x equals 1 minus e to the negative mx, gives the probability that something does not last as long, right? So remember, probability is 100%, right? And so if this one gives the probability of it costing more, then 100% minus this would be the probability that it does not last as long, or it costs less, okay? And then again, m is the multiplicative inverse of the mean amount of time. Okay? Exponential distributions are represented by this curve, similar to the one shown. Okay, the x-axis represents length of time, and then y-axis represents the probability that it's going to last that long. Okay, and of course, probability goes from 0 to 1. 0 meaning no chances, 1 meaning 100% chance. Okay, so in example 1, so the average length of time that a student at East High School spends talking on the phone per day is 1 hour. Okay, so that's the average or the mean. Okay. We want to know the probability that a randomly chosen student talks on the phone for more than 2 hours. So note that it says more than, and so as a result, we're going to be using the function f of x equals e to the negative mx, because it's more than. Right? Just store that because it's more than. Okay, then what do we need to know? So we want more than 2 hours. So 2 is going to be our x. Okay. Right. So we're really finding f of 2, the probability that it's going to be 2. Okay. Then the average length of time is 1 hour. Okay. So if the average is 1, the multiplicative inverse, or the reciprocal, which is m, is going to be, just flip it, it's still going to be 1. Okay. So then that's going to help me to plug it in. Average 1. And so then the reciprocal, which is m equals 1, then will be here. Okay. So it's going to be e to the negative 1 times 2. Okay. Type that into your calculator, e to the negative second power. And this gives you approximately 0.13534, or approximately 13.5%. So what's the probability that a randomly chosen student talks on the phone for more than 2 hours? About 13.5%. Okay. Okay, so why don't you try CYP1, and then once you're done, come check your answer. Okay, you should have gotten something approximately 0.26360, or approximately 26.4%. If you got that right, you can move on to the next example. If not, here is your explanation. Okay. So here, we want to see the probability that it lasts more than. So that's why we're doing f of x equals e to the negative mx. Okay. We want to test 4 years, so our x is going to be 4. Okay. And then here, since the average is 3 years, the reciprocal of that is 1/3, and that is what we plug in for m. Okay. And then e to the negative 1/3 times 4 power will give you this. Okay. If you got this part but didn't get this, it's probably a mistake with you entering the calculator, which you should really email me about, so that way I can show you how to type it into the calculator correctly. Okay, so moving on to example 2. So if athletic shoes last an average of 1.5 years, what is the probability that a randomly selected pair of athletic shoes will last less than 6 months? Okay, so here, keyword says less than, which means then I'm going to use this function. Right, so f of x equals 1 minus, right? Because if this is the probability that it's more than, right, that's the percentage, then I'm going to do 1 minus that, 100% minus that, it's not going to be more than, to get less than. 1 minus the probability that it's going to be more than will be less than. So 1 minus e is the negative mx. Right? So that less than tells me I'm going to use this formula. Okay? So we want to know less than 6 months, so that's what I'm going to be plugging in here for x. Okay. Here the average is 1.5 years. So if average is 1.5 or 3/2, right, that means the reciprocal to get m will be 2/3. So if average is 1.5, which is 3/2, the reciprocal of that is 2/3, right? Which is why in previous math classes we talked so much about converting decimals to fractions and fractions to decimals, etc., etc. Okay. So let me plug in what I know. So f of 6 equals 1 minus e to the negative 2/3 times 6 power. Okay, sorry. So since we're talking about years and 6 months is half a year, so it should be 1/2. Okay. So it's important to look at the units, right? 6 months, years, so then that's why x would be half of a year. 6 months is half of a year. Okay. And then this gives me approximately 0.28347, which is approximately 28%. Or 28.3%. Or the book makes it even more specific, 28.35. Okay, either way is fine. Okay, so why don't you try CYP2, and then once you're done, come check your answer. Okay, you should have gotten approximately 0.15352 or 15%. If you got that right, you can move on to our last example. If not, here is your explanation. Okay. So here we know that the average lifespan of a dog is 12 years. We want to know the probability that a randomly selected dog will live less than 2 years. Okay? So the fact that it said less than tells me that I want to use this exponential distribution function because of the less than. Right? And then since it's less than 2 years, my x is going to be 2. Average lifespan is 12, and the reciprocal of 12 is 1/12, so that's what I'm plugging in for m. Okay? So then type it into my calculator, and this is what I should get. Okay, moving on to our last example. Okay. So a chocolate company makes boxes of assorted chocolates, 40% of which are dark chocolate on average. Okay. The production line mixes the chocolates randomly and then just packages it 10 per box. Okay. We want to know what is the probability that at least 3 chocolates in a given box are dark chocolates. Okay. And so before we get fully into example 3, let's look at binomial distribution here. Okay. So in a binomial distribution, all of the trials are independent. Right, meaning what happens in one does not affect the other. Okay, and in a binomial, the reason why it's binomial is because it only has 2 possible outcomes. success or failure, what you want or what you don't want. Okay? The probability of success is the same in every trial, right, which makes it independent because what happened before doesn't affect my ability of success, so it's always consistent. Okay? And then the outcome of one trial, like I said, does not affect the probabilities of any future trial, so that's what makes it independent. Okay? The random variable is the number of successes in a given number of trials. Okay? So here, the probability of X successes, so the number of successes in any amount of independent trials is, or in a specific amount of independent trials, is the probability of X equals the combination of the number of independent trials and then taking how many successes we want, multiplied by P is the probability of success to the number of successes we want power, multiplied by the probability of failure to the n minus x power. Okay? The expectation for a binomial distribution is E of x equals np, so the number of trials times the probability of success. Right, so there you go. Okay, so with all that in mind, looking at number 3 again, okay, we want the probability that at least 3 chocolates in a given box are dark chocolate. Okay, so here, right, instead of doing probability of 3, 4, 5, 6, 7, 8, 9, 10, we can just take out the probability of what we don't want, right? So here we can instead do the probability. So the probability of more than 3 dark chocolate is going to be 100% minus the probability of having 0, minus the probability of having 1, and minus the probability of 2. Okay? The reason why we're doing it this way is because doing probability of 3, 4, 5, 6, 7, 8, 9, 10 will take longer. Okay? So there's a binomial this is binomial probability because it's either dark or it's not dark. Okay? The probability of success is 40%, so lowercase p, 40%, so that means that's 0.4. So this comes from here. And so then the probability of failure then, if 40% is success, that means 60% is failure, which is 0.6. Okay? So what we're going to do is find the probability of each. Okay, so 1 minus probability of 0. Okay? That means out of 10 chocolates, we're picking 0. Okay? And then its probability of success is 0.4 to the 0 power. Probability of failure 0.6 and then 10. It all fails. Right? Because remember, it is capital P of x equals NCX and then P to the x and Q to the n minus x. That's why. 0, 10 minus 0. Okay? So that's probability of getting 0. Okay? Minus the probability of getting 1. So 10C1. Okay? Then it'd be probability of success, so 0.4, getting 1 of them. And probability of failure then would be 9 of them, right? For a total of 10. Okay? Then probability of getting 2, 10C2. 0.4 to the second power, because 2 of them are successful, 2 of them are dark chocolate. And then failure, that would mean 8 of them are not dark chocolate. Okay. And then if we enter this all in, it might help to do it step by step. 1 minus. Okay, because of the powers and everything, that'll be too hard to write it all out. So I'm just going to enter it all into the calculator. Okay. And then I get approximately 0.8327, whereas the book says this is approximately 83.27%. There you go. Okay. So then the next part asks for the expected number of dark chocolates in the box. So remember, the expectation of x equals the number of trials times the probability of success. Okay. So then there are expectations of this. There are 10 trials. Okay, and the probability of success is 0.4. Expected number of dark chocolates per box is 4. So why don't you try CYP3, and then once you're done, come check your answer. Okay, you should have gotten 89% approximately. Okay, if you got that right, you could get started on your homework. If not, here is your explanation. Okay, so if 20% of the chocolates are white chocolates, what is the probability that at least one chocolate in a given box is a white chocolate? So probability of success would be 0.2, and then probability of failure then would be 0.8. Okay. So if we want at least one chocolate to be white, greater than or equal to 1 white, instead of doing probability of 1 white, 2 white, 3 white, 4 white, it's just easier to do 100% minus the probability of 0 whites. Okay. So that means in our 10 chocolates, we chose none of them to be white. Okay. And then so then probability of success 0, right? 0.2 to the 0 here. And then failure is 0.8 to the 10th, because 10 of them are not white. Okay? And then plug that into your calculator and you get 0.89263, or about 89%. So that's it for today. Have a great rest of the day. Bye, guys.